This section we're going to talk about some of the special types of relationships with trig angles, and we've already talked about particularly a few angle relationships with trig functions. That is every single multiple of 90 degrees and their values for every single trig function. And we could go all the way around a circle and keep going around, and every single multiple of 90 we could evaluate because we know those values by what we formulated in class. But now we're going to talk about two specific other types of angles, and what we're going to talk about first is, let's suppose we have an equilateral triangle. Now I say we have a side length 2. You might say, well, why don't I just say 1? Well, for right now we're just going to have it be 2. And you'll see why in a second. And it says, let's suppose we bisect one of the sides. We would have a right triangle with acute angles of what measure? Well, if I bisect this, and I make that a right angle, this is still going to be 60 degrees. Knowing properties of triangles, this angle being bisected has to be 30. So right now, what we have is a 30 degree angle, a 60 degree angle, and a 90 degree angle. And what this triangle looks like is this. If I cut it in half, I know that side's 2. And I know this is a right angle. And we bisected this, and this is going to be 1. So it makes more sense to say it as 2, because if I made this 1, we'd get a fraction here. Now let's suppose we wanted to talk about the ratios of this triangle. Now we don't need to talk about 90 because we already know the ones for 90, and we wouldn't use the right angle anyways. So let's talk about specifically these two angles. Well, we have two sides. We need this side here. So this is my missing side. This is, in the picture, the height. So I'm just going to call it y. So 1 plus y squared equals 4. I get y squared equals 3. So y is equal to square root of 3. So now I have the three sides, so I can say what the 6 ratios are for both a 60 degree angle and a 30 degree angle exactly. And again, I could have made this 4, I could have made this 10, I could have made this 50. It doesn't matter because in ratios, everything's proportional. So it doesn't matter what numbers I use the smallest number possible to make this very simple for us. Okay, so sine of 60 degrees, sine of 30. The sine of 60 degrees is opposite over hypotenuse, so the square root of 3 over 2. The sine of 30 is the opposite over the hypotenuse, which is 1/2. So now I have two more exact ratios using sine. If I use cosine, that's adjacent of the 1 over 2. Cosine of 60 is the adjacent of the, this is 30. It's the adjacent over hypotenuse, so that's the square root of 3 over 2. And again, this goes back into our cofunction type problem when we talked about cofunctions. They're the exact same but different angles. There's the 1/2, here's the 1/2 with 60 and 30. Tangent of 60, opposite over adjacent, that's the square root of 3 over 1, or just the square root of 3. The tangent of 30 is the exact opposite, or the reciprocal, 1 over the square root of 3, which I'm going to make the square root of 3 over 3. And the reason is because it's 1 over the square root of 3. So, there's the first three. The last ones we just have to write in terms of They're reciprocals. Cosecant is 2 over the square root of 3. So it's going to be 2 square root 3 over 3. Cosecant of 30 is just going to be 2. Secant of 60 is going to be 2, whereas secant of 30 is 2 square root 3 over 2. Or 3, excuse me. Cotangent of 60 degrees, that's adjacent over hypotenuse, or opposite. So that's 1 over the square root of 3, which is the square root of 3 over 3. The cotangent of 30 is just the square root of 3 over 1. So those are your 6 ratios for each 60 degrees and 30 degrees. And this is always true. For a 30, 60, 90 triangle, these are degrees. First of all, one leg is always bigger by a factor of the square root of 3. So what does that mean? Well, if this had been 4, this would have been 4 square root of 3. If this had been 10, this would have been 10 square root of 3. So this factor of the square root of 3 just is multiplied in because this is the bigger leg. The smaller leg is half the hypotenuse. It's half the hypotenuse. So whatever it is, it's the result of bisecting this angle. So I get half of this equaling the hypotenuse. And you can revert to this. The smaller leg is divisible by a square root of 3 compared to the bigger leg. The hypotenuse is double the smaller leg. So when I talk about this, the hypotenuse is 12. That means we bisected to get this one here, which is 6, the smaller leg. The bigger leg is bigger by a factor of the square root of 3. It's just how 30, 60, 90 triangles work. So if it asks you to find 6 trig ratios for an angle of 150 degrees, we have to look at this and say, well, that's going to be in quadrant 2. So really, if we construct a triangle, we're looking at this angle here. Well, if we're looking at that angle here, the question is, well, what angle is that? Well, that's a 30-degree angle. So really, it's a 30-degree angle in quadrant 2. So we have to go look at every single thing that we got from quadrant or 30 degrees, all of these up here, but then we have to ask ourselves, well, we're in quadrant 2. What's negative in quadrant 2? We got to look and ask ourselves, what is negative in quadrant 2? And the answer is everything except sine and cosecant. So everything that we got from the 30-degree, but the ones except sine and cosecant have to be negative. So when we say the sine of 150 degrees is going to be the same as the sine of 30 degrees, it's true. So the sine of 150 degrees would be what we got as the sine of 30 degrees, which is 1/2. and we do the exact same thing all the way, except making everything else that's negative in quadrant 2, just make that negative. For example, cosine was positive at 30 degrees, but it's negative in quadrant 2. So we do that for every single one for a 150 degree angle. And then the next one I'm going to talk about the other specific type of triangle and how that relates to the ratios that are unique to this.